go from there. So let's just see where we go with this. And Kyle, actually, what would help is as we go through the review, if as I'm going over the confidence intervals and the probability distribution, if you have a question, just stop me. But these are not going to be the questions that are on the assignment, but they're pretty close.
Right.
Yeah. So if you watch the video, if you pay attention here, you're certainly going to be on the right track.
Yeah. Awesome.
So for this week, we're kind of moving forward with doing some statistics by hand. We're not ready to jump in just yet to SPSS. I think a few students are having a little bit of trouble getting, SPSS might be on back order or having trouble getting it loaded. So we've still got plenty of things that we can review on the assignment this week. We're still working with one of our same data sets as last week, and it's asking us to do a confidence interval. And then, like I said, Kyle, we've got another student that had a question about probability distribution, so maybe we'll go over an example of that. But essentially, the kind of 10,000 foot view of confidence intervals. Sometimes in statistics, when we report a mean, so for example, somebody takes the ACT or the SAT, and we would report somebody's ACT as they scored a 24, and we know the max is 36. Or when they get their SAT score, and I forget what the SAT is scored out of, but let's say that their composite score was a 1600. Kyle, if somebody retakes the ACT or SAT, or even like for graduate school, the GRE, are they going to score the exact same the next time?
Probably not.
Probably not. The test versions are a little bit different, but if they take that test over and over and over again, they're probably going to start converging on their true mean or their true average. Well, sometimes in statistics, what we report is a confidence interval. So in this case, we have our Beachy head data. So we have some place where a group of people, 172 people, sadly committed suicide. It's made up data, but it's just sample data. And so we don't know, even though it's sample data, we don't know if that's encompassing the true population parameter. So essentially what the confidence interval allows us to do is we can give a better estimate. In this case, if we wanted a confidence interval around the mean, we can say that we wanted to be 90% sure or 95% sure or 99% sure that our true mean or our true average falls within a certain interval. So in this case, I would assume you've been working with your data, and let's work through this confidence interval problem, but you can easily plug the BG head data into Excel, and here's what I was coming up with. So this was probably fairly similar to what you were coming up with. You should have, when you pull your data in, 172 data entries. For your quartiles, we've got a median of 34 and an average or a mean of 36.16 with a standard deviation of 13.03. We're going to need this information right here, our statistical mean and the standard deviation, in order to calculate our confidence interval. So let's look at an example of this. Let's assume we wanted to create a 95% confidence interval around this average age of 36.16. So how would we do that? Well, you're probably noticing in the book that, and they probably gave this formula, but this is essentially what our formula is for a confidence interval. We're always going to have some observed statistic. Okay. In this case, it's asking us to calculate that 95% confidence interval around the mean. So this observed statistic is going to be our mean, 36.16. So it's an observed statistic plus or minus, and that plus or minus is going to give us our interval, that bandwidth around the mean. So it's the mean plus or minus, and then in parentheses here, we've got a couple of values that we need to come up with. A standard error, which a standard error is nothing more than the standard deviation divided by the square root of n. And then we're going to multiply that standard error by some sort of a confidence level table value. And so we're going to need to know how to use a critical values of t table. And we'll get to that in just a moment. So we already know some of these values. We know our observed statistic. We just said that was 36.16. We know our standard deviation. We calculated that up here in Excel. So students, as they're calculating that, can double check it, 13.03. And we know we have a count, or an N, of 172. So we can already start figuring our standard error, which is 13.03 divided by the square root of 172, which should come out to be 13.03 over 13.11, or 0.994. That should be our standard error. Now we need to calculate this right here. We need to figure out what our critical value of t is. So let's see exactly how we do that. Let's go here and I'll pull up the critical values of t table. Kyle, have you used a critical values of t table before?
Maybe it's kind of rang a bell, but I'm not sure.
Okay, so let's go in here. Oop. We've got one saved here, and it's probably in the back of our book. You can look them up online. I just knew that I have one saved here on my computer, but essentially they're all the same. They're not going to deviate from each other.
Mm-hmm.
But that critical values of t table is going to give us that critical cutoff point to enter into our formula. So we're going to need to know a couple of things. We need to know where we're setting alpha. That's our probability level. And we need to know our degrees of freedom. So let's go back to our notes and see how to figure out our degrees of freedom. In this case, our formula for degrees of freedom, oftentimes it's just how many ever is in our group minus 1. So n minus 1. So we had 172 data points here that we're working with. So 172 minus 1 would be 171. Now this table that I have here only goes up to 120. It goes from 120 to infinity. But what we're going to see here in just a moment is there's really not much of a difference between 120 and infinity. A lot of times, Kyle, in statistics, especially the social sciences, we oftentimes say that a 0.05 is our cutoff for alpha. So in this class, if I don't give you an alpha level in the question, just assume we're working with an alpha of 0.05. Okay. So we do two things here. We determine what our alpha level is. Usually it's always going to be a two-tailed test, unless, again, you're specifically told in the question or the information in the question suggests that it's a one-tailed test. Usually it's going to be two-tailed. So a two-tailed test at a 0.05 alpha level. So we're going to go down the column all the way to that point where we intersect with our number, our degrees of freedom was 171. But what we see here, these two numbers, if you can see that, if we had 120 degrees of freedom, our cutoff value there is 1.980. All the way up to infinity, our critical value of t is 1.960. So a very minute, very, very minute difference there. So we're just going to go with our 1.960 value. So we're going to need to remember that, 1.960. And where do we put that in at? That's our critical level table value here. Does that make sense?
Yes. Is
So
that 1.96 linked to the z-score at all? Where
well,
95% of the data was 1.96 standard deviations away?
Yes.
Okay. Is that the same essentially?
It is.
Okay.
Exactly. Yep. Yeah, that is linked to that. Okay, so we have here, now we have all the values that we need in order to calculate our confidence interval. We had our observed statistic plus or minus the standard error times our critical value of t. So we solve for, in basic algebra, what's in parentheses first. So the 0.994 times 1.96 should give us a value of 1.95. So the way we interpret this, Kyle, is it's our observed statistic plus or minus the 1.95. And a lot of times with a confidence interval, you might just see that it's reported this way, that a 95% confidence interval is exactly this. Other times they will say that we are 95% confident that the true mean falls somewhere between the ages of 34.21 and 38.11. Does that make sense how they came up with those two numbers?
Yeah.
Yeah, so they just subtracted and added 1.95 from 36.16. So here's the critical thinking question as a follow-up. Let's assume instead of, Kyle, that I asked you or other students in the class, okay, instead of a 95% confidence interval, what if I wanted you to calculate a 99% confidence interval, you know, in capturing that population mean? Do we think that that confidence interval would be more narrow around this mean, or would it be wider? Any thoughts on that?
It would be more narrow because we're more certain that the mean falls somewhere in the population mean.
Okay, so let's back up a second. Let's just intuitively look at that. So that's a good guess, and I think that's what many students might say. But let's just intuitively say that I asked you, because we've been dealing with a lot of probability questions in this class. You flip a coin, you have the probability of getting heads or tails at 0.5, right? 1 out of 2 times you're going to get heads, correct?
Yeah.
So we say you have a 50% chance. Assume I asked you, hey, you only want to be 50% confident that you're going to capture the true population mean. Only 50% confident. That's like a coin flip. Do you think that bandwidth around this mean is going to be super narrow because we only want to be 50% confident, or is it going to be super wide?
It's going to be narrower.
You got it. You're exactly right. We don't need to be as confident. In that case, we're saying we only want to be 50% confident, right? If we said we wanted to only be 10% confident, like we could give such a small bandwidth around that mean. So if we went the other direction, right, and now we say we want to be 99% confident, this bandwidth here is going to be a little bit wider.
Right.
So that's kind of how that works. So you might be asked in a statistics class maybe to find a 90% confidence interval. Usually it's going to be like 95% or higher. So maybe 95% confident, 99% confident, or even 99.9% confident.
Okay.
Those tend to be in this, especially the social sciences, are 3 alpha levels, 0.05. So if we go back here and we look at our alpha levels, 0.05 would correspond with a 95% confidence. A 0.01 means that 99 times out of 100, we're going to be confident in our results. And at the 0.001 level, that corresponds with being 99.9% confident.
Okay.
See how that works?
Yeah.
Great. So on this assignment coming up, you are asked to determine a confidence interval around some observed statistic. So it would be fairly similar to what you and I just calculated right here. Okay. Some other questions had come up, so about probability distribution. So let's work through a couple examples with that and see how you're doing with that. Still working with our Beachy head data. So if I gave you the question, what's the probability of someone over the age of 60 committing suicide at Beachy head? One of the things that I do, Kyle, when I'm first going to do a probability distribution problem is I want to visualize that data. So that here it's asking us, what's the probability of it being greater than the age of 60? So I want to visualize that on my normal distribution and really make sure that I shade in the part of the distribution that I want to solve for. So in this case, and this isn't drawn to scale, I don't know exactly how many standard deviations 60 is above. It doesn't really matter at this point. We're just trying to generally visualize this. So this is asking us the probability of someone over the age of 60. So we've got 60 here, and so it's asking above the age of 60. Now, one thing that I want to clear up, and I saw a couple students do this on their assignment, they said 61, because technically I did ask for over the age of 60, but theoretically, this scale, I mean, this distribution right here, any one single point under this distribution, so just this of 60, if we were to ask the question, what's the probability of someone the age of 60 committing suicide? When we went back and watched the videos, the probability distribution videos, the presenter did a much better job than I could do of describing that any one single point under this line, this super, super small finite line, it's a probability of 0.
Mm-hmm.
If you calculate it out, it does come out to be such a small value, it approximates 0. So in theory, in probability distribution, we can only get ranges. So that's why we say 60 or older, or maybe I say, what's the probability of somebody committing between the ages of 30 and 60? We can get a range there, but not for one finite value. So if I were to say over the age of 60, it's the same thing as saying 60 or older.
Mm-hmm.
So that's just one point to clear up. But I think the important thing is can we visually display our graph right here? So we're definitely not trying to solve for all of this under the curve. It's from 60 and above. And I think that's one thing, if students will take the time and draw out that graph and visualize what they're trying to solve for, that can cut out on some mistakes as you get into the later part of the problem.
Mm-hmm.
So what we need to do first is create a z-score, right? We need to create a z-score for this and for figuring out our probability. So we need to convert this single value to a z-score. And to do that, our general z-score formula is whatever our data value is. It's an x minus our mean. So in this case, 60 minus our mean of 36.16 divided by our standard deviation. That's going to allow us to standardize our scores and essentially convert our mean to a z of 0, so that everything under this distribution is standardized.
Mm-hmm.
So you should, on this example, if I were asking you to create the probability of somebody over the age of 60, you should create a z-score of 60, and that should come out to be approximately 1.83. And then we need to find out, and we need to use our z-distribution table to then figure out, all right, well, what's the probability associated with that z value? So I'm going to have you walk me through this. So we just came up with a z-score of 1.83.
Mm-hmm.
So how do I determine the value under the graph using that z-score? What do I need to do?
You would start in the far left-hand corner under the z-scores, go down, scroll down to find positive 1.83 right here. And then since we're working, so then you go over to the fourth column right where your mouse is to find the table value.
Yep. So we've got 1.8, and we follow that over to the hundredths position of 0.03 and where those intersect. Great. We come up with a value of 0.9664.
Mm-hmm.
And so that is the value that we are going to put back in here, our z distribution. So our z distribution of 1.83 is equal to 0.9664. And so I visualize this out here, and if we go back to our z table, that's exactly what this shows us. Our table is showing us that all of these values here in our table is for everything to the left of the line, right?
Yeah.
So we need to make sure that we understand that, and that this z-score of 1.83, that this value of 0.9664, that's everything under the curve here. We're not solving for under the curve here, are we?
No.
We're solving for this tiny portion under the curve. And we know that the probability associated with any value always ranges from 0 to 1. All of that probability under the entire curve, all of that adds up to 1. So if we take 1 minus that value of 0.9664, we should get everything under this tiny portion of the curve, everything to the right of that z equals 1.83. And that should come out to be 0.0336. So if we were to kind of write this out intuitively, therefore, the probability associated with someone over the age of 60, given our data set, someone over the age of 60 committing suicide at Beachy Head is 0.0336, or in other words, about 3.36%. Make sense?
Yes. And this might, and you might have already covered this, this area underneath the curve, that visually represents probability, correct?
Correct. Yes.
That's 3.36% of the area under the curve.
You're right.
Okay.
Yep.
Or
Exactly.
are we gonna build on that with like statistical significance? I mean, I feel like I did a whole semester of undergrad and college on just p-values and alphas.
That's what all this is building up to, is to be
Okay.
able to understand what a p-value means, and why when we say, if we're testing two groups and is group A significantly different from group B,
Okay.
why we set alpha at like 0.05 or 0.01. Yes.
Okay.
That's exactly what we're building up to.
It was all starting to kind of run together, and I was like, oh, this is okay. This is what we're building towards.
There you go. Yep, exactly. So one more example there, and we'll kind of fly through this one. So what if I asked you sort of the probability associated with someone between two ages? So between the ages of 45 and 60, what's the probability of them committing suicide at Beachy Head? So here again, what do we do? Well, we're going to visually display our data, right? Probability of 45, and we're solving for this, our x. The probability of somebody older than 45, but also younger than 60. So that area under the graph of what we're solving for is this tiny area here, from 40 to 60. Fortunately, we've already solved for everything under 60.
Right.
Essentially, we just need to solve for everything, the z-score associated with 45. We've already walked through those steps, but if we get a z-score for 45 given our data, that z-score should convert to 0.6784. And if we look that up in our z table, the z of 0.68, a z of 0.6, and we go all the way over to 0.8, as long as I did that correctly, 0.7517. So let's check to make sure I did that correct. So we get a probability. So the probability of everything under this part of the curve for a z of 0.68, which is equal to somebody age of 45, that's 0.7517. So now we have our two probabilities in order to figure out this range. We're solving for x between 45 years old and 60 years old. So we just said that we had already found the probability under the curve for that age of 60, which was everything up here, right? Everything under this curve. And now we just solve for everything under this part of the curve. So we should just have to find the difference between the two. So the difference between that 0.9664 and 0.7517 should give us 0.2147. So our final answer there is the probability associated with somebody at Beachy Head solving for x of being older than 45 yet younger than 60. That probability should be 0.2147, or about 21.5%.
Okay.
And yeah, you're absolutely correct. That is all building up to really understanding how probability and establishing alpha works um, for inferential statistics.
Okay. Another question I know
Yeah.
somebody asked me this and I had it too. When we drew our histogram out of that beachy head data,
Yep.
so they're like, well, it doesn't look like normally distributed. It looked a little skewed one way. That
Right.
doesn't matter. Were we just supposed to assume it was normally distributed?
For something in the general population to be perfectly normally distributed is probably fairly rare.
Right.
In this case, yes. I mean, absolutely. I mean, I could pull that up, but yes, you were correct in that it probably was not perfectly normally distributed. Um, yeah, it was certainly skewed positively. So let's make sure that I do understand that. I think I've got that down. Yep, right here.
Yeah.
We had some extreme scores out here, and I think this person was like 84 years old,
Yeah.
somebody in their upper 70s. We could probably argue that this is somewhat normally distributed
Yeah.
out to here.
See that
Not
now.
perfect, but certainly we've got some extreme scores.
Okay.
Pulling this data, the tail of this to the right, which we call that positively skewed.
Mm-hmm.
Yep.
Okay. Got it.
And we will get into in this class as we move forward. There are tests, statistical analyses that can be done to assess is something normally distributed enough to I assume that it is normally distributed.
Okay. Got it.
Makes sense.
Mm-hmm.
Okay. Did you have any other questions? Anything else you wanted to review?
No, not from there. I was good.
Okay.
So.
Well, hopefully that review of confidence intervals and probability distribution kind of gets you going in the right direction for
Yeah.
this week's assignment. What we'll do next week is we'll continue with our review, but also next week we're going to kind of start getting into chi-square tests as well.
Okay.
So we'll have some videos that we'll go over for that.
Okay. Sounds good.
All right. Well, good work. And yeah, we'll talk to you soon.
All right. Sounds good.
All right. See ya.